Safety has always been a paramount concern when working with and around electricity. The fact is, almost everyone who works with electrical equipment has had some sort of electrical safety training. Even the inexperienced has, at the very least, a simple understanding and respect for what electricity can do if it's not handled properly. Why then are people still being injured or killed each year in accidents involving electrical equipment? In this series, we'll take a closer look at the reasons why, in spite of all the safety-related training we receive, people just like you are still being hurt or killed in electrical accidents. We'll look at real reasons why otherwise well-trained people get hurt around electrical equipment, and what you can do to keep it from happening to you and the people you work with. Let's begin with a basic look at the hazards of electricity. Most people are aware of electrical shock. Electric shock affects human beings in three ways. It affects the function of the heart. It can injure body tissues. And it causes the muscles to contract. Each of these effects is potentially serious or even life-threatening, depending upon the conditions under which the shock occurs. The human body's movement and all of its internal functions are regulated by minute electrical impulses moving through the nervous system. Your heart beats because of a steady, rhythmical pulsing of electrical signals that tell it when to beat. This is what medical personnel measure when, for example, they test the heart with an electrocardiograph. An external electric shock can interfere with heart function by causing fibrillation, a disruption of the heart's rhythm that can cause death within minutes. As little as 50 volts of alternating current can cause this to occur if skin resistance is low and the resulting current flows through the chest area. Another aspect of electrical safety is the use, care, and maintenance of personal protective equipment. In this segment of our Electrical Safety for Industrial Facilities series, we'll look at the types of personal protective equipment in use today. You'll see that each piece of equipment is designed for use within certain voltage ranges and arc exposures. And you'll see how to care and maintain personal protective equipment, and how to test it to make sure it can do the job that it is designed to do. Personal protective equipment can be grouped into three general categories: temporary insulating equipment, arc protective equipment, and energy detection equipment. Let's begin with temporary insulating equipment. This group includes rubber gloves, rubber blankets, and devices such as protective sleeves, rubber line hoses, and covers to fit over bare conductors. Keep in mind that none of these pieces of equipment is intended to provide permanent insulation. It's important also to realize that although this equipment is quite effective, it was originally designed primarily for the utility industry, with its pole-top method of distribution, and generally wide distances between bare conductors. The National Fire Protection Association 70E and the American Society for Testing Materials Volume 10, Section 10.03 provides guidelines for the in-service use and care of flexible insulation protective equipment to ensure the safety of the electrical worker. Many safety practices that are perfectly acceptable in the utility environment are not sufficient for commercial and industrial power systems. Industrial and commercial electricians should realize that their power systems are different from utility power systems in three significant ways. We have been using electricity for over a century now. We understand it. We work carefully around it. So why are people still being hurt and killed by electricity? We are hurt and killed because in the commonplace world of the industrial facility, and even in our homes for that matter, it is surprisingly easy to forget just how dangerous electricity can be. As we've mentioned earlier in other segments in this series, the most common electrical injuries are caused by arcs and shock. Understanding the effect of electric shock is so important, we want to examine some basic information on how electricity behaves and how shock can result. 120-volt low-voltage shock kills more people than any other voltage because it is one of the most common voltages, but also because it is very easy to underestimate what such voltage can do. To review what we learned earlier, injury from electric shock depends on several factors. The first is current. Expressed in amperes, current is the amount of electricity flowing through the body. The second factor influencing injury is electrical voltage, which is the driving force behind the flow of current. The third factor is resistance. Virtually anything that electricity flows through provides some resistance or reduction of current. Glass or ceramic offers great resistance. Copper wire or water, very little. The fourth factor is time. The human body's muscle functions are regulated by nerve impulses, which mean we are literally controlled by electrical circuits. These circuits are disrupted by outside electrical shock, and the longer they are disrupted, the greater the likelihood of injury or death. Working on or near exposed energized circuits and equipment can be extremely dangerous if proper safe working practices are not followed. Working on energized equipment should be done only after all other avenues to de-energize the equipment and circuits have been exhausted. There are times when it becomes necessary to work on energized equipment because it may be more hazardous to de-energize it. Hazards associated with de-energizing equipment include shutting off an emergency alarm system, shutting down the ventilation system to hazardous areas, or shutting off the lights to a process area. Under these conditions, the work must be performed by qualified persons using proper procedures, protective equipment, and protective measures in order to perform the work safely. But doing so is very serious business. De-energized work can be as hazardous as energized work because many times only part of the power system is usually de-energized. Voltage or voltage feedback from another part of the system contribute to the hazards of de-energized work. In this program, we'll take a look at the special problems of working on a de-energized system and how to address them. We'll demonstrate how to isolate or clear parts of an electrical system in order to perform work safely. We'll see what an effective lockout-tagout procedure calls for. And we'll find out how to select and then safely install a temporary ground. First, why is de-energized work potentially so dangerous? As we mentioned earlier, usually only part of the power system is de-energized, leaving the rest of the system hot. Proving that part of a system is